For those that don't know me, by the way, land surveyors? A lot of land surveyors, okay. And how many use real-time positioning? Okay. Yeah. About 18 years ago, I asked that question, and there was one guy in the back that went like this, and that was it, So can we see that we are in a confluence of technology? Can we see that? What is it? What's real-time about? It's about communication, really, isn't it? It's about communication. So we have cell networks now. We can use real-time networks. We can use real-time networks where we have cell technology. We also have great hardware now, better software now, and we have a whole lot of new signals and constellations of satellites up there that are now what we would call our truth. I got to thank these guys, the C4G, for getting me down here, Steve also, and Tim Osborne also. They paid my freight down here and paid for my room for a couple nights and everything. Actually here on my own, kind of representing National Geodetic Survey, but they didn't pay for any of my travel, so I appreciate the support. And for those that don't know me, I'm a land surveyor registered in Maryland. I've been surveying for around 44 years, almost ready to hang it up, not quite. And been working with the NGS around 6 years as a geodesist. Or as my wife said when I was hired, what's a geodesist? I said, I don't know. But so I've been using real time since the mid-90s, and things have changed a lot. And I'd just like to mention Dr. Roy Daka, who made the first contacts with us to get us down here and everything. In memory of him, great guy. So here's the crux of the matter, and you guys know it. When I say guys, I mean it generically. You folks know that. What is truth? And that's what real-time positioning is all about. What is truth? Is it the marks in the ground, or is it the antennas in the air? And we'll be talking about that as we go through all this. Well, we're moving away from the marks in the ground to the antennas in the air, and that's what real-time networks are all about. A couple slides on this. In about 10 years, those marks in the ground will only be secondary access to the National Spatial Reference System. They will not be primary access. We'll be getting our elevations. I'll use orthometric heights and elevations interchangeably if that's okay. We'll be getting our elevations from the antennas in the air, not the marks in the ground. And we know sometimes you got to use marks in the ground. You got to. You got to set them, or you got to use them, or you got to find them. You got to rely on something that is the truth in the ground, right? For your projects, for anything you're going to do. Can you trust the antennas in the air? Well, we're working that way. That's the whole question. Very forward-thinking document from the Flood Protection Authority. Says use GolfNet for your elevations. Very forward-thinking. And it'll work with the best practices. Real-time positioning is not as good as geodetic leveling, but it's a lot faster and a lot cheaper. What kind of accuracy do you need? Do you need millimeters? You're not going to get it from real-time positioning. So what do you do? Well, can you use real-time positioning for a project? Sure. You bring your stuff into your job to 2 centimeters, then you do your digital leveling to make your project very precise. That's what it's all going to be about in 10 years. And we can do it now as long as we know what to trust, what is truth. And it matters. If you use single base, is it okay to talk about single base positioning too, as well as the network today, a little bit, hopefully? We still use radios and CDMA modems or something for single base positioning. You guys still set up base stations and do that? I'm seeing some yeses, so we'll talk a little bit about that. Louisiana, thanks to Tim Osborne for these slides. And this is what's going on. You guys, probably more than anyone, I said guys again, you folks more than anyone know about this. You know how marks are destroyed. You know that marks move. You and the folks in California know this real well. And we're talking, almost a centimeter a year. in a lot of places, or more than that, really. So Louisiana's had a bunch of different level runs and different height mod projects, and there's still problems. There's still problems. So the most important thing that you guys have to decide, you folks have to decide, is what is truth? Hopefully, in the end, GolfNet will be the truth. There we go. So changes, okay, that's the calculator that I took my party chief test in 1970. And you know, things have changed quite a bit. You know, if there's a tan button there, but I didn't need that because I worked outside. And there was a sin button, and I kept hitting that one, but nothing was happening. Anyway, you know, of course we got a tablet computer in the field now, right? 30 years later. Things have gone like this in 30 years technologically. All right, we've gone from high labor intensive surveying, or positioning, if you will, in the field with 4 or 5 people in a crew to one person with a real-time rover. So how important is it that that one person knows what the heck he's doing or she's doing? Very important. The truth is always in the field for the guy with the pole. It's a little bit slow, I apologize. Whoop. So, GPS receiver 30 years ago, 5 channels, 2-seat coupe, convertible, 300 pounds. The Rockwell Collins Generalized Development Model to test the GPS constellation in 1970, whatever, 7. And of course now the rover with a modem built in, and the, you know, the 200 and some channels, you know, things like that. Just in 30 years, this is how it's changed. I guess I'm going to have to hold this up like that. This is me 30 years ago. This is how we did it with an old K&E. We did differential leveling. Gravity? The heck is gravity? We don't use that. We did our whole county. I worked for Baltimore County government back then for 31 years. And we had a control network based on a local control. In the center of Baltimore City, George Washington Monuments nose or something like that was 00, you know. And it went northeast, southwest from there. So you had negative coordinates and positive coordinates. But it was all just pulling the tape along the ground, you know, and then running this kind of levels. So guess what happened? You know, you can imagine what happened 30 years later when 2 lines crossed. You had, you know, a foot difference in the elevation or whatever. Of course, now digital automatic levels, great stuff. Our constellations are going from GPS, maybe 31 birds up there right now, to multi-constellations. We have GLONASS that we use now. It's fully operational. Galileo in Europe, Compass Beidou in China. All these constellations are adding to what we can use, or what we will use. In 10 years, there'll be about 115 satellites up there or so that we can use. I'm sorry. Not sure what's going on here. I don't remember hitting a button. There we go. And as we walk around, right now, Steve.
Point at that and it'll work.
Okay. Okay. I know, I'm just kidding. You work. All right. So, okay, autonomously right now we walk around, and what do we have, 3 meters, 5 meters, something like that, you know. Well, in 10 years we'll have half a foot walking around autonomously by using all those constellations and signals. We'll have a new geometric datum. We'll have a new geopotential datum. And it's going to be a different ball game. Probably doing a lot more with GIS. We'll probably doing indoor positioning, underground positioning. There's going to be a whole lot of stuff going on in 10 years. So I'll probably, hopefully, be on a beach somewhere. But there's a lot of people here that'll be using this technology in 10 years. So we need to know a little bit about it. Let's change this to this slide. GPS is up in the air about 12,000 miles, okay? There's about 31 satellites up there. Everything in GPS is based on XYZ, a Cartesian XYZ coordinate system. There it is, okay? The origin's at the center of the Earth. Then X is through the equator, Y is right-hand coordinate through the equator, Z is through the pole. That every satellite sends out its information in the ephemerides in XYZ. All right? So somehow we get from XYZ to Louisiana State Plain South. Okay? But we use that. A datum. Here we go. Okay. Apologize. Anyway, a geodetic datum has a surface, which we call the ellipsoid. What is the ellipsoid? It's something that best fits the world, mathematically. Okay? If you tried to fit to the ground, it wouldn't work too much. It wouldn't look real nice. So we have a mathematical surface for a geodetic datum. We have an origin. We have an orientation. So we have the 0 for the longitude through near the Greenwich meridian, right? We have an equator for an orientation that way. And then we have a scale. How big or small is that surface? Okay, so that's our geodetic datum. There's a lot of geodetic datums, all right? The GPS system uses WGS-84, Department of Defense. What it does is it inclines 55 degrees from the equator for a line of satellites, okay? Then every 60 degrees around, the declination's 55 degrees, every 60 degrees around is another line of satellites. 60, 120, 180, 240, 300, 360. So what you end up with, these are the lines of the satellites, and they've recently moved them around so we have better coverage during the day. But what that means is 35 degrees either way from north, there's no satellites. Right? If you incline 55 degrees and swing that around the circle, there's nothing up there. So you're going to set a point. That's all right, it's fun. If you're going to set a point, you're going to set it with a pole to the north, aren't you? Because there's no satellite that's going to block. So if you take a quarter of that surface, and you have XYZ, right? All the satellites are in the WGS-84 datum in XYZ. And you take that circle, and you can create then a longitude, latitude, right? I don't have a pointer. You know, the longitude from this meridian, the latitude from the equator, right? And now you have a height component, the ellipsoid height, right? That's the difference between where you are and where that mathematical surface is, right? You can be below it, and you usually are near the coast. Hey, thank you, Cliff. Too many moving parts. Just a second. There it goes. Yeah. Oh, you just push it in. All right. So, you have this new height component, which you can't see on the screen very well, can you? Okay, so GPS now gives you a height, ellipsoid height. When that first came around, we first started using GPS, nobody thought that you'd be able to use that height for anything. You know, it wasn't even an issue. So they had to readjust the control in the country to the HARN, High Accuracy Reference Network, because they had 5, 10 centimeters, you know, these, and then people started using this for height. So now we've got a system that gives you a height component. One of the problems we have is that our national datum, NAVD3, isn't geocentric to a couple meters, 2.24 meters. However, the world and the Department of Defense uses something near the geocenter of the Earth to a couple centimeters. So what does that mean? It means that between what we use and what the world uses is about 1.5 meters in height, that ellipsoid height. And that's an issue to understand. It doesn't matter too much now as we walk around autonomously because we're not that accurate. We're 3 meters, 5 meters. In 10 years from now, you would see that. You would see that difference. But don't worry, we're going to change the datum. So here's an example. 1.365 meters difference between NAVD3 and ITRF. International Terrestrial Reference Frame. scientific datum. The Department of Defense uses a datum called WGS-84. They started out aligned to NAVD3, and then they moved 4 times over the years, essentially defining a new datum every time to be within a couple centimeters of ITRF. So therefore, the GPS satellites are now sort of aligned to the International GNSS Service 08 datum and the ITRF 2008 datum. Our Department of Defense is close to these guys, not our national datum of 983. Just something to know, something to understand, and what's going to change. So let's just think about this. We got a system in the air that's based on a datum called WGS-84. We've got our national datum, 983. We've got a scientific datum called ITRF, which actually uses 4 things to get its positions, including very long baseline interferometry and Doppler orbitography and satellite laser ranging. Then you've got the International GNSS service that just uses GPS stations, okay? And then you've got a vertical datum, NAVD 88, that we use right now, based on marks in the ground. The way that's propagated is either by geodetic leveling, which is the most accurate way to do it, or height mod procedures, okay, that will publish it to a couple centimeters. But we're not worried about that, really. We're worried about getting accurate elevations with real-time positioning. There's no way to put that into the NGS database right now. You can't do real-time positioning and have it be part of the NGS database. That being said, if I'm out working on a job, I'm going to use real-time positioning. But what am I going to start from? What's the truth, right? That's the whole question. So, and then of course we don't work in the curvature of the Earth in longitude and latitude. We work on projections of that surface flat, right? So we can work in state plane or UTM or something like that. So we work on a map projection of a datum. All those things are part of what we're doing with real time. So 983, ITRS, WGS-84, IGS-08, and the new datum, I don't know what it's going to be called. I'm just going to call it NRS 22, okay? Vertical datums 29, 88, and a new vertical datum in 10 years, maybe NAVD 22 or something like that. I'll show you what that means. And then our projections, state plane, universal transverse Mercator, or LDP, low distortion projections for a particular project. Are we going to keep the state plane coordinate system in 10 years? I don't know. Probably. I don't know. It would be nice to have some kind of projection everybody uses. Oh, righty, I did the wrong thing. There we go. So what the latest iteration of our national datum, 983, has gone through some changes. Not a new datum, just a new adjustment, a new realization of the same datum that, remember, is not geocentric to a couple meters, right? So the last one is 2011, Epoch 2010.0. The biggest change to that is it updated the positions by 8 years, because our previous realization was CORS 96 Epoch 2002. Now it's Epoch 2010. So 8 years. They're using absolute antenna heights now instead of relative antenna heights. They have a better idea about velocities of how the stations were moving over time. So we've got a new adjustment of 983 that we use now. The passive marks were readjusted and published recently with local accuracies and network accuracies. What does that mean? Well, the network accuracies are how they're aligned to the datum. The local accuracies are how they're aligned to the closest stations in the same project that was done. Okay, so the local accuracies are going to be better than the network accuracies generally. So let's see what we have here. We have an old, sorry, I don't know if this is going to work or not. Can't really see it. You have an adjustment of NAD 83 2007, the previous adjustment. Okay, the new adjustment then, and you have a network accuracy here, north, east, and the ellipsoid height. and this is in centimeters. Remember the old data sheets where you had first order horizontal and, you know, second order horizontal and all that? That was length based. So many parts per, you know, 1,000 meters or whatever it may be. There's no length based positioning with GPS. It's all in a position error ellipse. So that's why they've switched to this kind of thing. So now you have a position error, not a length-dependent error that you have measured with a total station or something. Has nothing to do with that. So the new data sheet has moved some stuff up above that line. You see the ellipsoid height, the date, the epoch of the ellipsoid when it was taken, the orthometric height. And I use this example for Maryland because Louisiana has very few that have an orthometric height, as you know. And you've got now network position errors, and you've got local position errors. That's the new data sheet. Okay? So is that truth? I don't know. It might be. But the only thing we know about that mark was the last time it was occupied and put into the database. Could have been 30 years ago and just readjusted into the new realization. The marks in the ground are only as good as their stability over time, right? And down here, that's not so good. The antennas in the air, you know every single minute where that antenna is. If it moves, you know. If it subsides, you know. And that's the advantage of having active reference stations, like GolfNet. So here's the local accuracies, I think. No, that's superseded control, I'm sorry. Here's some of the local accuracies to other points that were tied to it. New data sheet, okay, that's what you'll get now when you look at the data sheet. All right, so the next geometric datum, NAVD 3 is dumped. No more NAVD 3. The new datum will take that offset, that bias that by a couple meters, and it'll pick a certain epoch of time to the worldwide IGS datum, let's call it. And it'll move the origin over to that point. So what does that mean? It means now we're actually at the Earth geocenter, and we're actually at the center of where the satellites are orbiting, because the satellites don't orbit 2 meters off the center, right? So we're going to move it over. Once we do that, it's a new datum. And then what they'll do is they'll pick a certain epoch of time, give it a position in the International GNSS Service datum, and then give a conversion so that we use it here. The question is, do we fix it on the North American plate? NAVD 3 is fixed on the North American plate. So that means while North America, as you look at it, is moving like this, everything's moving together. As the world looks at it, North America is moving like this, and South America is moving like that, and Europe's moving like that. They take an average of all those plates, and that's how they define their parameters for their datum. So do we do that, or do we fix it again like we did with NAVD 3? I asked that question last week, and nobody knows yet. So I can't give you an answer. But I can tell you that that's a question they have to resolve. Personally, I would rather have it fixed on the plate. Then at least you're relative to some known points in the continental United States or like that. You know what you're dealing with, rather than have, if you didn't fix it to the plate, you'd have to deal with velocities every time you did a survey. All right, well okay, where am I now? Then you have to apply the velocity to the coordinate to get where you are now. So that's the bias it would remove. Now, as far as the vertical datums, the vertical datum of 29 was supposed to be kind of a mean sea level datum, and they took 26 tide stations, 5 in Canada and 21 in the United States, and they made them 0, more or less. They said, well, here's sea level, all right, it's 0. All right, we're going to level from there, and we'll level over here, and that's 0, so we'll just balance our levels out between them. Well, that didn't work too well, because sea level is not the same everywhere. There's a lot of factors that affect that. There's Cliff has an excellent presentation on the C4G site about subsidence and about these different things. So I'd recommend that you guys look at it. But anyway, here's some of the differences between NAVD 88 and 29. Now, what's happening well, you can see it better in the color slide, is this is 88 minus 29, okay? So in the eastern part of the United States, 0 for 88 is here, 0 for 29 is above it. Western. Yeah, 29's, yes, sorry. 88's here, 29's here, so that when you subtract them, you have a higher value for 29 than 88, and you get a minus. Western side of the country, just the opposite. And around Louisiana, did I show that? Yeah. Around Louisiana, they're almost the same, almost. I don't know how much it is here, but here's the 0 line here. Okay, so you have to be a little bit careful about that too, what datum you're using. There's a lot of legacy data, I'm sure it's in 29. All the FEMA flood maps used to be in 29. Hopefully they've been updated. No? They're still in 29. So that's what you have to be careful with. In Maryland, Baltimore County had the FEMA flood maps converted to their own vertical datum, which was 1.8 feet different than NAVD 88. Do you think there were some houses built wrong in the floodplain for that? Yes. Because people would come from Pennsylvania, they come into Maryland and get the flood map and look at the elevation, okay, NAVD 88, okay, and they'd set their control and they'd build the house and 1.8 feet wrong. So you have to be careful about that. And of course we know that tide gauges, again, Cliff covers this excellently in these PowerPoint. But you use a tidal epoch of 18.67 years. Why do you use 18.67 years? Because that gives the moon a chance to go through all its nodes, which is the biggest influence of gravity on the tides. Also, it gives you a chance to average out the major storm events over that time, so that you come up with a mean sea level over the 18.67 years. The current epoch runs to 2001. So we're working on another one, but it's not, of course, in effect till 19 or 18. So anyway, you can relate the tide gauges to the datum in NAVD 88. This is the importance of having a core station somewhere around. An active reference station like GolfNet or whatever, you know where that antenna is always. So if it subsides, you know it. What does that tell you? That tells you whether the water is rising or the ground is sinking or both. You can't tell if the water is coming up the shoreline whether the ground is subsiding or the water is rising just by looking at it. If you have an active station near it, you can tell that. That's the importance of an active station. You know where it is. And it's important in Maryland, like in Louisiana, mean high water determines the private ownership line. And when you have flat land near the water, 1 foot in elevation makes a really big difference in your property line. So it's very, very important to know that you're always using the same criteria when you establish something. It's a tough thing to do in Maryland. I'm sure it is here too. All right, so the new vertical datum, NAVD 88. Why don't we just keep 88? Well, there's errors across the country. It's not gravimetric. Therefore, we can't just use a geoid model to get elevations or orthometric heights. Well, then why don't we start over and just re-level? Well, 2 things. Number one, it would cost a couple $1 billion. And if anybody has enough, we can maybe do that. And the other problem is, with every passive mark that's ever been put in the ground, there's always a chance of it subsiding, of it getting wiped out, of it being disturbed without you knowing it. There's no metadata about that monument that we know. With an active station, we know. So the whole purpose of the new datum is to base it on gravity. If we can base it on gravity, then we can use an active reference station and a geoid model to get an orthometric height, an elevation. Okay, we can do that now with our geoid 12 and our geoid 09, but it's a hybrid geoid. It's not a gravimetric geoid. It doesn't follow gravity, which means it doesn't define an equipotential surface. Okay, so By doing that, we can build a 1 centimeter accurate geoid, gravimetric geoid, across the country. By flying, we've already flown the Gulf Coast. They're flying the rest of the country, and they're getting gravity data. They'll establish a gravity surface at whatever they decide to hold, and that'll be 0 for the new datum. But it'll be a gravity surface. Therefore, if we can do that to 1 centimeter, and you can bring it to your site to 1 centimeter air after that, you can bring the national datum to your site to 2 centimeters with one setup using GPS. You've got the national datum to 2 centimeters to your site. That's pretty cool, especially in an area of huge subsidence and disturbance that you have here. So, yeah, okay, you've got to run a sewer line, and you know it's 1% grade, and that's not accurate enough. Yeah, right. Well, remember what we said, you get your digital level out, and you do your precisions based from that elevation. But you've got the national datum that ties to everything in the world, you know, to 2 centimeters. And that's pretty good, 6/100ths of a foot. Okay, so that's the idea. That's the new datum, using active stations to establish orthometric heights. And that'll be in about 10 years. Here's the distortion in 88. It's over a meter error as you go across the country. So that's one of the problems. We have to build a geoid model to take that into account, so that the folks in Washington State can use ellipsoid heights from GPS, and the folks in Maryland can use ellipsoid heights from GPS and use a same model to get an orthometric height. So that's the problem with 88. Leveling for the new datum goes away. And this is what it's about for those of you that haven't seen this. Remember, we get, can't do it. We get ellipsoid heights, little h, from GPS, right? We're given that. We go out and set up, we got an h. Well, if we knew the difference between that and NAVD 88, we could just combine the two and get an NAVD 88 height on the ground where we are. So that's what N is. N's a geoid model. Right now it's geoid 12. Yeah. But it's geoid 12 now. And in some areas like the East Coast, it's wonderful. It's great, you know. Not so good here. So you're using a model, essentially a gravity model, of surface gravity to take from the datum to the ellipsoid. And then you get the ellipsoid height when you work. Combine the two for your elevation. And you can do that with single base, with a network. There are problems with using that. You have to be careful. So when you use the new adjustment of 83, 2011, you should use geoid 12. If you use 2007 or CORS 96, use geoid 09, because the ellipsoid heights are different. Don't mix them. Make sure you use the right one with the right geoid model. Okay? Now, here's the problem. And I was talking with Randy before this session. This doesn't show everything either, apparently. Apparently there's other smaller areas of distortion. The areas in pink are saying, don't use geoid 12 here, there's a problem. Well, they just found this out a month ago. I don't know what the answer is. I thought originally that maybe the geoid model problem was by holding the wrong elevation, wrong orthometric height on certain benchmarks maybe. And that distorted everything and put the error between them or something like that. Maybe. Bay of gravity data? I don't know, I doubt it. And Randy said there are a lot of clumps of areas, urban areas especially, that have benchmarks that were heavily constrained. Well, if there's any play in those benchmarks, that's going to distort the whole adjustment. You know, if you hold something fixed, you better be sure you want to hold it fixed. That's true no matter what you do. But by holding something in error fixed, you're distorting your adjustment. And maybe that's what's happening here. So, that being said, this is, if you look if you look at that head on, if you're looking at Maryland from west to east, there are 3 geoid models represented here. Not the new ones, but when this was done, they were new. So you've got geoid 96, 99, 03. If you put 09 there and 12 there, what you would be looking at is a bias between them. But look how they compare relatively. Okay, relatively, they're almost the same, aren't they? Almost. And we'll be talking about relative differences, holding something as truth. Okay, you can use those models, any one of those models, if you hold something as truth. If you have a mark in the ground, if you have something in bedrock or something in a bridge abutment that you're sure hasn't moved, and that's truth, you can use any geoid model from there, because relatively to that point, it's going to give you the right answer. Also, yes, sir, please.
I want to back up a minute. You said that using geoid, if you're using the latest epoch, the 2010 epoch.
I'm sorry.
You said if you're using the 2011 epoch, to use geoid 12.
Yes.
Now, if I was going to do post-process adjustment, then I get that, okay, if I want to use the geoid 09, which I'm going to use in South Louisiana, I need to use cores 96, 2002.
Correct.
How do I get those positions from core?
Okay. For the actual core stations, they're still available. Even after they're not available online, you'll have superseded control that you can get them from. If you look at the passive marks in the ground, they should also have superseded control NAD 2007. 2007 is the passive nomenclature that's used with cores 96. Okay? So those two are compatible. Difference between 2007 and cores 96 is cores 96 is the core stations themselves, just the core stations themselves, and they're truth. 2007 is the core stations weighted plus all the GPS campaigns on passive marks thrown in too, like 70,000 marks. So there's going to be a little bit of difference between those two, but it's only a couple centimeters difference. Okay? Yes, Cliff?
At the last annual LSPS meeting, I gave the transformation parameters to go between cores 96 and 2011 for the state of Louisiana.
Good.
If you didn't get a copy of it, email me and I'll send you those 7 parameters. But the difference between the two is a couple centimeters.
Let me go ahead and ask a question now, because I think we're getting close to a break time.
That's probably true.
Okay. At the Southeast Louisiana Flood Protection Authority, we noticed a problem with our heights on the new construction that the Corps of Engineers was performing. The Corps discovered it and brought it to our attention. And we had our own contract surveyor go out to verify elevation. What they seem to find, and as you say, we never know what the truth is, but we only know what we measure. But they seem to find that if they did a core solution, OPUS solution, I'm sorry, they did an OPUS solution, or if they did a static with known marks, they got one value.
Mm-hmm.
If they used the RTN,
Mm-hmm.
and it didn't matter if it was a GulfNet
Mm-hmm.
or SmartNet,
Mm-hmm.
they got a different solution, and the difference was about 4 inches, 4.5 inches. And I haven't had anybody be able to explain to me or to the authority why that's so. All we know is that these two pieces of very expensive flood protection failed to meet each other about 4 inches.
There's a plethora of reasons that may be so. So one reason would be that OPUS only has a certain precision to maybe 5 centimeters, maybe. Okay? So if you have 1/1500ths of a foot error to begin with, that's a good solution. All right? So first of all, you've got 15 hundredths, or let's just say 5 centimeters. It could be 10 centimeters. It could, from an OPUS solution.
Okay, well, the OPUS solution, if you're talking about a decimeter, that's right at the error that we
Right. That's a possibility, okay? Anything that you do, we'll be talking about this, anything you do with real-time or OPUS, I don't care which it is, if you want to hang your hat on something, you need redundancy. You need more than one data value on a point. If it's topo, no, I mean, you live with that. You know, you do it as a total station, you take a bad shot once in a while. But if it's an important point, you need redundancy. That's the first thing. The second thing is OPUS is going to give you a different answer than leveling. Now, OPUS if you're talking about an elevation, an orthometric height, OPUS uses your ellipsoid height while you're set up there. Remember the ellipsoid height, right? And it uses the model, Geoid 09 model. Well, there's errors in that model. And the thing that worries me the most is finding truth in southern Louisiana. That, to me, is the hardest thing that you guys are facing. Finding truth. What is truth? I don't know. You know, how do you verify a mark in the ground? You know, you can use the real-time network to do that. What is the real-time network going to use? It's going to use a geoid model to give you an elevation, right? If Geoid 12, if Geoid 12 has problems, you know, you're not going to rely on that. I asked back in the office, and people seem to think that Geoid 09 would work. I'm here to tell you that any geoid will work if you use it relatively. If you can hold something that you know is good and just use it relatively, it's going to be okay. Now here's the second thing. What I did was I actually took Geoid 12, okay, and I found out what the geoid value was, the separation at a certain point, all these points that you see there. Then I went 1 mile away to the west and did the same thing. This is the difference in the geoid separation 1 mile apart at all those points. So what does that mean? I mean, we're talking sub-centimeter in most of them, a couple of millimeters in some of them. Some of them are a centimeter or so, 3/100ths of a foot, okay? You can't do real-time positioning any better than that. If you can't live with a centimeter in real-time positioning, you shouldn't be doing real-time positioning. Okay? And 4 different ways to look at it. But what I'm trying to say is, by looking at those last couple slides, that any geoid model will work relatively. And if you use it 1 mile apart, you don't even have to use a geoid model. You can just use the difference in ellipsoid heights. What's your error going to be? Your error is going to be 5 millimeters, 1/100th and a half in a mile. Okay? 3/100ths down here. 2 millimeters, it's less than 1/100th of a foot, a mile away. So if you've got a small job, and you've got a point on that site that has been used for plans, and you know that the last set of plans was only a year ago, you're going to use that mark, right? Because you've got to have something you get to start from. So you're going to use that. Now, if you hold that elevation, you can actually just use the difference in your ellipsoid heights from that elevation to get your other elevations a mile apart. Now, I'm not saying every point in between that mile apart is homogeneous, but I think it is. If you look at the topography in that area, there's no mountains and there's no huge valleys. Everything's pretty flat. So what I'm trying to say is this. Take your choice of any one of those 4. But what I'm trying to say is, if you're doing a project, it doesn't matter what geoid model you use, as long as you use it relatively. Conversely, it doesn't matter to use a geoid model. Use a difference in ellipsoid heights in a small area. Okay, now when you expand that and you go from project to project to project, yeah, you got to worry about that. Okay, so you have to consider that too. But that's the same problem you have with state plane coordinates. You do a job in state plane coordinates, And I can tell you, in Maryland, there's a lot of plats that have been recorded with state plane coordinates on them that were based on ground distances. Not a big deal, but when you do section 1, then you do section 2, then you do section 3, and 10 years later you're on section 4 tying in, and you've got a 1.5 foot bust in your coordinates, then you should know why. So what I'm trying to say is, small jobs, relative values using GPS work. Okay?